Hey there, students. I wanted to do for you an example of an optimization problem from section 5 of chapter 4. So I'm looking at number 22 on the practice problem list. And so let's go through this problem together. And so I actually copied over the text of the problem into a writing program. So I'm going to switch over there. So practice problem from 4.5, number 22 says, a storage shed is to be built in the shape of a box with a square base. So I'm going to sort of draw, because I need to do that myself to keep track of things. So I have a square base box. So that means the top is square and the bottom is square. So I'm going to make a square here, and then I'm going to draw down just to suggest that I have a box here. So here's my box where, because the top or the bottom is square, I know that the four lines for the sides of the very top are all the same, but the height of the box might be different. So I'm going to just fill in some variables for that now, just to keep track of what they mean when they talk about the shape is a box with a square base. That means the sides of the base are the same. I'll call those X. But that the height of the box may be different, so I'm going to call that H. So the top is an X by X square, the bottom is an X by X square, and the sides are possibly taller. All right, so it says it is to have a volume of 729 cubic feet. So translating that means that volume is 729 cubic feet. Then it talks about the concrete for the base costs $3 per square foot. The material for the roof costs $6 per square foot. And the material for the sides costs $4.50 per square foot. So depending on which surface of your box you're making, the materials have a different cost. Find the dimensions of the most economical shed. So we want to find the dimensions. That means, in terms of my picture, I need to find X and Y, because we don't know the sides of the base, which is a square, and we don't know how tall the box will be. Those are the dimensions. And for when they say the most economical shed, that means lowest cost. That'll be in some number of dollars, I think, because everything's given in dollars per unit of area. All right, so that's what we're tasked to do. We need to find X and Y so that when we look at the actual dimensions and add up the cost to make it, we get the lowest cost possible. And so in an optimization problem, you focus on the thing you want to optimize. So we want to optimize the cost. And that means we want to express the cost as a function of a single variable so that we can then use our max-min derivative stuff on that function to find its minimum value. So to optimize the lowest cost, we want to optimize C function. So we have to express the cost C as a function of a single variable. All right, so let's try to go in a little bit more with what we're given. So we are told the volume is 729. So given the volume is equal to 729 cubic feet, but I know from my definition of X and H that this is equal to the length times the width times the height, which in this case is X times H, or we'll simplify by saying X squared H. So X squared H is equal to 729. I'm going to put that result here just to put it in a box. All right, so that gives us a relationship between X and H, the sides of the square base and the height of my box. And what I want is minimum C value, minimum cost, where the cost can be calculated by multiplying the square feet of each surface times the cost of which surface I'm talking about. So let's go through. $3 per square foot for the base. So the base down here, base area, would be equal to x squared. And so the cost of the base would then be $3 times x squared. So there's the cost of the base. I'm doing the base first. So then what other cost do we have? So then it says the materials for the roof is $6 per square foot. And the roof here is also going to be x squared because the roof square matches the base square. But the price is higher up there, so we're going to add $6 times x squared for the cost of the roof. Then finally we have the sides, and we want to get the cost of the sides. So there's 4 sides going around the box, and each side has an area. Whoops, didn't mean to erase there. Each side area is base times height, which is xh, x times h, and there's 4 of those. So that's going to be 450 times 4 times xh. So the total cost of this box is $3 times x squared for the base, $6 times x squared for the roof, and $450 times the 4 sides, which are each x times h. And we want to minimize this. So this is our function we want to optimize. The problem as it's written now, and I can simplify it a little bit, but the problem as it's written now is that it has 2 variables in it. It has x and h. So let's go ahead and simplify this by combining the like terms. This is 9x squared, and 4 times 450 is 18 times x times h. And we want to minimize this. Well, the way that I get this in terms of a single variable, so I can take the derivative and set it to 0 while looking for minimums, is I do a substitution. So I have 2 equations, and I want to get rid of one of the variables, so I could try to get rid of h or x, so I can express c in terms of only one of those. And looking at the equation we had for the volume here, it seems easiest to solve that for h and do a substitution. So from this, I get that h is equal to 729 divided by x squared. And then I'm going to take that and I'm going to substitute that into the other equation for the cost, because that will eliminate the h variable, and then it will be only in terms of the x variable. So if I do that, then I get the cost written purely as a function of x is now 9x squared plus 18 times x times 729 divided by x squared. So now I have a function that's only in terms of x, and now I can try to minimize the values of this function by taking its derivative, looking for critical values where the derivative is equal to 0, etc. I'll simplify this a little bit. So I have 9x squared, and I can cancel the x that's multiplied by the 18 with one of the x's in the denominator that's x squared, and I can multiply 18 by 729. And if I do that, I get 13,122, still divided by x. So that is my cost function that I want to minimize. All right, so how do we minimize that? We look for critical values. Now, we could talk a little bit about the domain of this cost function. Clearly, x cannot be a negative number because it's a size of a side of a roof or the base. But you could make x very, very big by making h very, very small. You could make x very, very small by making h very, very big and still have that same fixed volume. So we'll just say that we know that the x value is greater than or equal to 0. That's kind of an obvious restriction that we can place on x. And with that, I'm trying to minimize, so I'm going to take the derivative of the c function. And these are just powers, so we can just use the power rule. 9x squared, if I take the derivative, I get 18x. And when x is in the bottom of the fraction, that's like it's to a power of -1. I can use the power rule. The -1 comes out front, so actually I shouldn't have written a plus, leaving me with minus 1, 3, 1, 2, 2. And then the power on the x goes from a -1 to a -2, so that means this is divided by x squared. So there's my derivative function. And when am I going to possibly find a minimum value for this function? Either at the endpoints, which I really don't have any endpoints. Actually, I shouldn't have even said that it can be 0. So I'm going to take that off. X has to be greater than 0. It can't be equal to 0 because then I got no volume. And it could be very, very big. So I don't really have any endpoints. So really, I need a local minimum, which will happen at a critical value. So I'm going to set my derivative equal to 0 and solve for x and see where we might get a local minimum. So setting equal to 0 to find critical values. All right, so let's do that. So if I set this to 0, I can add that ugly fraction to both sides. And I get 18x is equal to 1, 3, 1, 2, 2 divided by x squared. So color coordinate here a little bit. I'm going to clear fractions by multiplying both sides by x squared. And anticipate of solving for my variable, I'm going to divide both sides by 18. And so if I do that, then I end up with x cubed, and 13,122 divided by 18. Well, I got that by multiplying 18 times 729, so I should get my 729 back. So then I can solve for x by taking the cube root of 729, and if my memory serves me, that's a 9. 9 times 81 is 729, yes. All right, so what is x? X is the length of one side of the base or the roof, so this would be in feet as a units. And I did have 729 cubic feet because that was the volume, so it makes sense that if I take the cube root of cubic feet, I get feet, so that's making sense. So I've now found one of my dimensions. Now, I could try to confirm that this only critical value is a minimum instead of a maximum, that costs go up when I change from the value 9, that's really the sweet spot. And one of the simplest ways to try to see that would be graphically. So in advance of this problem, I did graph the cost function. So this function over here, which was equal to c of x, if you graphed that cost function to see if it makes sense that 9 feet is a minimum value of that cost function, you should get what I put over here. Somewhere I have my Desmos. You get this graph. If you see here, I entered into the Desmos calculator 9x squared plus 13,122 over x. And I get this function, and you can see it does some stuff over on the negative side, but on the positive side, it's kind of like a big U shape. And if I go to the bottom of that, then you can see the minimum value is at 9. And so actually our derivative has shown us what Desmos would also show us. And it even tells us what the minimum cost will be, because this is the cost function. So when you set the base to be a 9 by 9 base, you're going to pay $2,187 for your box. But let's get back to the problem. Whoops. So let's see if this has gone away yet. No, it's still there. Good. So I can try to type this in. All right, so the first thing they wanted is it said, let x represent the length of one of the sides of the base and c the cost of the shed. What is the objective function? So I did come up with that. Let's see if we can get some credit on this problem by entering that in. So the objective function was 18x squared. I can do that like that, I think. Yes. And then that was going to be, yeah, that's good. So where do I find a plus on this little calculator thing? Let's do keyboard. Whoop, that was not the keyboard. All right, I'm going to do it. Pull out my keyboard so I can enter this value in. I'm sure it's on here somewhere. So plus is there. Let's go in here. Plus, and then I think I had 13122 divided by x. Okay. Okay, incorrect. Write a function of the cost of the shed, find the surface area of each component, multiply by the cost. I think I did all that. So let me see if I copied over wrong, just to double check. 9x squared, 13,122 over x. Next, I said 18x squared instead of 9x squared. Okay, I do have to copy correctly, so that's always good to check. Let me put this back in here. If I can back up there. Okay. So let's see, how do I back this up? Okay, delete, delete. There we go. Let's put in a 9, and hopefully now that I've copied my function over correctly. There we go. Okay, so then it says the interval of interest of the function is, so interesting. Type your answer in interval notation. I'm going to go for this. I really don't see how we can have any restriction other than to just go all positive numbers. So I'm going to go, there we go, from 0 to infinity. That symbol's there. Whoops. Oh, did it in twice. There we go. And close. So that's what I think they want. Let's find out. Okay, so they want the interval. I put that in. So then the length of one side of the shed's base is going to be 9 feet. And the height, I didn't get that relationship. So let's see. The height was, let's go back to my little formula. So the height is equal to 729 divided by x squared. So it looks like it's coming out to be a cube. So I'm going to use this thing here. And so height is equal to 729 divided by x squared. And in our case, x came out to be 9, and this is 9 cubed. So it looks like they're all 9. So that's going to be 81, which is a 9. Would have been more interesting if it wasn't a cube. If you changed the costs, I think you would get something different. But nonetheless, it is what it is. So let's go back over here and say that that's also equal to 9. Put the 9 in. 9. 9. There we go. And that's it. So this was the work description for how we got the answer. This led us to the fact that h is also equal to 9 feet because they did want the dimensions in the end. And so this is my write-up for this problem. So hopefully that's helpful. It does take a while to do a good job or write thoroughly on a word problem. That's the nature, and this is a good example. In general, for all of these optimization problems, you should look at the thing that they are asking you to optimize, which was in this case the cost economics of the shed. So that means lowering the cost. Try to express that function initially, maybe with more than one variable. Try to find a relationship between the variables. Often that leads to a substitution so that you can get the cost function in terms of a single variable. And once you've done that, then you can do your derivative analysis to find out the minimum or maximum of the objective function. So that'll do it for now. Keep up the hard work, and best of luck.